Too much. Okay, so this is section 3.3. I'll come back and answer questions on 3.2 if there are any later date. I got to get this to you all out today so that you've got something to do during the break. Anyway, I want you to look at these things. We're going to look at them rather quickly because I want you to notice some things. You have this polynomial right here that is the function, and you find its derivative using this definition. Then you expand the polynomial, you distribute everything, and negative in that, you climb, all the things drop out, take h into each term, and you end up with the limit as h approaches 0 of 4x plus 2h. And that equals 4x because h goes to 0. Right? Okay. Would you agree that if this is the one you start with, this squared polynomial, that you do all those same things, it's a little bit lengthier because there's more places to plug in x plus h, and there's more things to distribute that negative to. But as you keep going, you take h into each of these terms, you get this. And if you let h go to 0, that middle term disappears, and you end up with this. We're okay with that? This one's a little tougher. Sorry about that. Hope you didn't get dizzy in the move there. I don't know if you can see this very well, but in this one right here, we have a polynomial in the denominator. So what we really have is a rational function. But we do the same thing, replacing x with x plus h there, and we find a common denominator, which is this. Well, actually, I FOILed that out. And then remember my h over here. And then I multiplied the top of this one by x squared minus 3, and the top of this one by this, distributed the negative, multiplied by the reciprocal of that, 1 over h. All those guys added out. I took h into each one of these things, ended up with this. Let h go to 0 at this point. It feels like that's a lot of stuff down here, but it doesn't make division by 0. This goes to 0, this goes to 0, and what I end up with is 2 of the x squared minus 3's. And up here, with the h going to 0, I end up with negative 2x. So, is that okay? On this one right here, if we have just the plain old square root of x, the limit as h goes to 0, and I put these things up here. And notice that I kept the original definition of the derivative. I could have gone with the alternate definition, which is f of x minus f of a over x minus a. I just stuck with this one. Still, I rationalized the numerator in this form here. And when you do that, you take this times this, you get x plus h minus x, the x's add out. And in the bottom, when you multiply that, notice that I did not FOIL it out or distribute the h. And the h that remains after losing the x's cancels out, and I end up with 1 over this thing that I multiplied by. And as h goes to 0, I end up with root x plus root x, which is 2 root x. So y'all follow the algebra that was behind all those things? It's kind of tedious and arduous. What I want you to notice is instead of all the junk in between, I want you to notice how that compares to that. See if there's some sort of pattern. And some of you already know it. Please don't ruin it for the others. So I want you to notice how the original function is related to the derivative. Take a look at this one. That original function, and see if there's something about this that could lead you to this without all this crap in between. And over here, this one's a lot tougher. As a matter of fact, I'm not going to look at that one yet. But this one is tougher than those two. But perhaps you'd be able to see how you get from there to there, maybe. And because we've already spent quite a bit of time trying to get Gavin registered, I'm not going to let you think about it for too long. I'm going to tell you. If you take this, first of all, I need to show you what this is and why it leads to this in a very specific way. If you take 2x squared plus 3x to the 0, why did I write that? You'll see in a minute. That is what it is. I mean, anything to the 0 is 1, right? Okay, so that's the same expression as that, but you're going, why would you write the x? There's a reason. So if you take this right here and you take this exponent in this term right here, you take this exponent times this number, you get 4. And then you reduce this by 1 and you get 4x, right?
That's cool.
And then you take this guy right here, you take 0 times 3, you get 0 times x to the negative 1 if you reduce that, but still 0 times something, so this just goes away. It's not there. This is called the power rule. It is not It is not a theorem. It's a rule. It's a way of getting from here to here without this, and it works every time. And there's a proof of it in there, but I'm not going to show it to you. You're just going to take it and run with it. So you take 2 times 2, which is 4, and you reduce the exponent that you just used by 1. Anytime you have a constant, the derivative of any constant, if you think about it, the derivative of any constant is 0, because if you have a constant function, you go, that's not a constant function. This piece of it is. If you have a constant function, y equals 3, what's its slope all the time? 0, and that's what you're hunting for. So constants, the derivative of constants terms is always 0. The derivative of power terms is power times coefficient reduce the power by 1. Look, it works here. 2 times -3 is -6. Reduce the power by 1. This one right here is understood to be a 1. 1 times 2 is 2. Reduce the power by 1. It goes to x to the 0, which is 1. So this derivative was -6x, this derivative is 2, and this derivative is 0.
Miss Jake?
Yes.
So if you have like a super long function that was a pain in the butt,
Yeah.
could you, just looking at what this does, just find the derivative of every piece of it?
Piece meaning term? Yes. Term, not factors. That's a whole different thing. If you got several things multiplied, like in this parenthesis, you got one function and you're multiplying by another, that doesn't apply. But if they're all terms, each term can be derived separately. Each term is its own function. Okay? It's like saying f of x plus g of x plus h of x. Find all the derivatives and combine them. It's the same thing. So as long as you're doing terms, it's okay. Now, this one over here, that's the power rule, and it doesn't apply to this one. You'll see why in just a minute. I'll talk to you about that one in just a minute, but I want to go clear over to this one instead. This one's a little bit stranger than those over there, but when you see this, you can be able to apply the power rule to this too. Watch this. If I take that original function and I rewrite it this way, then the power rule will apply to this too, but you have to be careful. F prime of x, if I apply the power rule, is going to be 1/2 times 1, x to the -1/2, because that has to be reduced by 1. That goes downstairs because it's got a negative exponent, so it's 1/2x to the 1/2, which is 1/2 root x.
Oh, that is so cool. Wait, so what's the reduced by 1? Where does that come in?
That's when you do the multiplying, when you take the power here times the coefficient, then you get this times this goes in the front, but this always has to be reduced by 1 to apply the power rule. And 1/2 minus 1 is -1/2, which gives it a negative exponent, which shoves it downstairs, which turns back into this radical.
Oh, because you're taking one of the 1/2. Okay. Yep.
Did you follow that?
Yeah, I just didn't understand why you have to take one out, but now I do.
Okay. This one's a different ballgame. This one you're thinking, well, I could just take x squared minus 3. I could just take that up and make it x to the -2 minus 3. No. You are not allowed to move terms up. Only factors. If you had things that were multiplied, then you can do things switcheroo all the time and make all your exponents positive. But if it's minus or plus something here, this thing is stuck, and so you got to come up with something else. Because this won't apply. The power rule will not apply to this.
Gosh, dang.
So there are other rules. Okay? There's the product rule, and the quotient rule, and the chain rule. The chain rule is a whole section by itself. Now, we have already done, take a look, on page 116, we have already done rule number 1. The derivative of any constant is 0. We've already done the power rule. Every time you do that, you take the exponent of each term, one term at a time, exponent times coefficient, reduce the exponent by 1. The constant multiple rule. I haven't shown you that one. It's not a big deal. It'll show up. You'll see it. I'm not even going to show you that one. It's kind of a dumb one. It's already been incorporated in here. We just haven't given it a name. If you have several things being added or subtracted, you can take the derivative of each individually, which is what Jacob and I discussed. Turn the page. If you look at example 1 right there, example 1 says find dp dt. Don't worry about the crazy. It's usually dy dx, but ours is dp dt because it's p in terms of t. So just get used to the notation. It says to find dp dt, which means find the derivative of p with respect to t. And if you apply the power rule to each piece, you get 3t squared plus 12t minus 5/3. Everybody seeing that quickly? Cool, that's awesome.
This is cool.
Example 2 says finding horizontal tangents. The question is, does the curve y equals x to the 4th plus 2x squared plus 2 have any horizontal tangents, and if so, where? We're going to do this algebraically. You could graph this and find them, but we're going to do this algebraically because it brings home why the calculus can be so important, this derivative business. Because learning where functions turn when they stop increasing and start decreasing and vice versa, if you think about that with me for just a minute, if you take a curve, like a polynomial curve of some kind, I don't know where it is, like this, can you see that this thing has a horizontal tangent here at this x? It has a horizontal tangent here at this x. And it has a horizontal tangent here at this x. I didn't draw that very well. And it has one here at this x. Because that's when the thing here stopped increasing and started decreasing. It decreased for a while, stopped decreasing, started increasing. It can be very, very useful to know where a function quits increasing and starts decreasing, or vice versa. And that is where the derivative has a value of 0.
Oh, so you just derivative.
Oh.
So you find the derivative and set it equal to 0, and it will tell you the x values for which there are turning points.
So it's really the max and min.
Yeah.
Of the derivative.
No, using the derivative, it's of the function.
Yeah.
Okay, so consider this. We got x to the 4th minus 2x squared plus 2. That's f. Now I want to know where the turning points are, or where the maxes and mins are. So I need to find the derivative, which is what now?
X. 4x to the third.
Good.
Third
Minus 4x to the.
That's it. Okay, and we want to know where it's gonna. So we set the thing equal to 0 is what we do, and now we have to call on our algebra skills. First thing you should do when you're trying to find the zeros of a function is factor out what you can. Good.
We've seen that before.
We have.
X plus x.
4 is 0, so you can be ignored. X will be 0 when the value of x is 0.
1, negative 1.
1 and negative 1. So if you were to graph this original function, it would have turning points at 0, 1, and negative 1.
Okay, that is awesome. Let's try this.
Later, we will have an entire section dedicated to this idea, and you will be able to determine whether these are max. You should be able to anyway, because you know the behavior of this graph. It's going to start high and end high. So it should have a minimum at negative 1, a maximum at 0,
Well, apparently, if there's
and a minimum at 1, because you know the behavior of this curve. So the first one that shows up on the left, it's got to be shaped like this. It's got to start high, and it's got to end high. And in between, it's got to hit the very first thing on the left, negative 1 here, and here, and then 1 here. So but because you know the behavior of the graph, you should know that the first occurrence is a minimum because it starts high and ends high. And the next occurrence is a max, and the next occurrence is a min. There are other, whether it's a max or min, and it's a calculus way, but there will be a whole section dedicated to that. What we wanted to know is where on the x-axis does the tangent, is the tangent flat? So you set the tangent equal to 0 because that's where your horizontal line has a slope of 0. It's at those turning points, and it occurs at. Anyway, I'll move on from there because we've got more things to do here.
Quotient rule, that looks terrible.
Yeah, well, we got products and quotients, and they are a different kind of ballgame. So we are going to do the product rule first, and I will show you the product rule as I do an example. So I want you to turn to example 4. The product rule is stated in very formal ways on the previous page. It also gives you a proof as to why it works. If you're interested, read the proof. It doesn't take very long. I'm just not going to prove it to you. We're going to go to example 4, and we're going to find the derivative of a function that is the product of two derivatives. I'm sorry, the product of two functions. My mistake. So, can somebody read it to me?
X squared plus 1, in parentheses. X cubed plus 3 plus 1.
X cubed plus 3?
Yes.
Okay, let me show you one way that you could do this. Now, they don't all lend themselves so easily this way, but this is an easy way to show you why that the product rule does work. What I'm going to do before I derive it is FOIL it out so that I can have a polynomial to apply the power rule to. I just taught you that, right? So we can figure out what the derivative is. So this is going to be x to the 4th plus 3x squared, but that's going to belong down here.
The first one is 5th.
X to the 5th. Yeah, you're right. X to the 5th. This one right here is going to be, x to the 3rd. Oh, I know what I was doing. Let's put my 3x squared back here because I want my x to the 3rd to lead out here. So it'll be plus x to the 3rd here, and then plus 3.
And that 3x is squared.
Yeah.
Yeah, 3x squared.
Yep, it is. Thanks. Now are we good? And things are in order, right? I don't usually do it out of hours. I make a lot of mistakes. So now that we have it as a polynomial that I just taught you how to take a derivative of, what's its derivative?
5x to the 4th plus 3x squared plus 6x.
Done, right? Okay.
So much faster.
Now I want to do it right next door to this. I want to do the very same one here, but I'm not going to FOIL those out. I'm going to show you the product rule and convince you why it works. So I'm not going to FOIL them out. I realize I've got one function times another, and here's how you find the derivative directly. It's the first function without doing anything to it times the derivative of the second function, which is
3x squared.
good. And then plus. When you do products, it goes to plus, just like logarithms.
Plus
Logarithms,
the other way around. Oh.
products and sums are related. Then you do the second one without changing it times the first one. First one's derivative. What is it?
2x.
Okay, so I want you to see what we've done. We took the first of the product, we took this one times the derivative of this one. First times the derivative of the second. Plus, because products go to pluses. The second one, write it down as is, times the derivative of the first. So there's two terms. In each case, one of them stays the way it is times the derivative of the other. Did you switch places? First times the derivative of the second, plus second times the derivative of the first. I have never seen a calculus book except for ours that actually writes that out as a quote. If you look on page 119, right in the middle of the page, just before Gottfried Wilhelm Leibniz, it says, you can remember the product rule with the phrase, the first times the derivative of the second, plus the second times the derivative of the first. Mathematicians don't like to write stuff like that, but every single calculus student who's ever lived knows that phrase. Why not print it? So that's what it is. Anyway, if we clean this up by distribution, we get 3x to the 4th. Is that right?
Yeah.
Did I write this right? Yeah. Okay. 3x to the 4th plus 3x squared plus 2x to the 5th, no, 2x to the 4th plus 6x. Yeah? Which is 3x to the 4th.
5x to the 4th plus 2x to the 4th. Are we moving it around?
Oh, yeah, 5x to the 4th. 5x to the 4th plus 3x squared plus 6x.
Whoa, wow.
So that's evidence that the product rule works because when you FOIL it out and do it with the power rule, you get the same thing.
I think it's still faster to do the first one, though.
It depends on the function. You're right. You're right. This is 6 1, half dozen the other about. I mean, you may find this easier to do than this, and that's great. But if this function is a log function, this is a sine function, you don't want to do it that way.
No, you.
Okay? So the product rule can be very useful. This is just, they just did it with a couple of polynomials to show you the two different ways to do it lead to the same derivative. To show you that this works. So when you have the product of two, it's the first times the derivative of the second plus the second times the derivative of the first. Okay, now I want you to look at example, no wait, we're going to do the quotient rule next. Quotient rule is a bit more involved. Okay, and you're going to have to take this one on faith because again, I am not going to take the time to prove it to you. The proof, however, goes very much like this one we haven't addressed yet. It's just in a general way. Okay, so I want to show you what the quotient rule is. It says this. guess you guys need to get used to the notation. So I am going to show you this. The derivative with respect to v of u over v. No, sorry.
Respect to x. Respect to x.
Is it with respect to x? Yeah. Yeah, the derivative with respect to x. You're right. Of u over v. Now we have to very clearly understand in our mind what u and v are. They are functions that are written in terms of x. But we don't care what they are to talk about the generalities here. This is a function written in x. This is a function written in x. It's one function over another function. Okay? Not necessarily polynomials, but one function over another. So this is a function written in x, and this is a function written in x. In order to expedite the rule here, we don't care what the actual functions are. This is just a general idea. The derivative is equal to the bottom function times the derivative of the top one minus the top one. Minus because it's a quotient. Quotients go with negatives. There's a little more to it than that, though. The top one times the derivative of the bottom one. All over the bottom one squared.
The whole function squared.
The entire function squared. This is one of those cases where you don't FOIL it out, ever. You always leave it in factored form. Just a little square on it. Just leave the square on it. Don't FOIL it out. Okay, now, this one's got a really kind of a sing-songy way of remembering it. And practically every calculus student I've ever met knows it. This is what it says. And it's not, you don't actually sing it, but it's sing-songy. It says, listen, low, d high means derivative of high. Low d high minus high d low over low low. Low d high minus high d low over low low. That'll kind of stick in your mind if you want. Low d high minus high d low over low low. That's not quite the way he prints it here. I never learned this sing-songy type. I learned it from someone else. But when I was doing calculus, we memorized it with this thing right here. It says, next to rule number 6, it says you can remember the quotient rule with the phrase bottom times the derivative of the top minus top times the derivative of the bottom all over the bottom squared. That's what I memorized. But the sing-songy will help you remember. It'll stick in your mind better because it's kind of weird. Okay.
The calculus part.
That's gonna be in my head all day now.
We'll have a performance. Be like, what the crap? What?
Okay, let's try and apply that to this one and see if we end up with the same thing that the definition did.
Whoa. So yeah, this is two functions. What is minus?
F prime of x is going to be the bottom times the derivative of the top, which is
Zero.
0.
Yeah.
Minus
I love
the top times the derivative of the bottom,
3x squared.
all over the bottom square, which is what?
Negative 3x squared over x
Uh-oh,
cubed
I
minus
screwed
3
up.
squared.
Oh,
The different
no.
problems.
Well, that's the derivative of this one, but that's not what I intended to write down. We'll do that one. We'll do that one too. Come up with it. But
Okay.
it's going to be negative 3x squared over x cubed minus 3 squared. That's going to be its derivative. Now, let's do it the way I intended, which was to do that one using the.
Just change the
quotient
3
rule?
to a 2
Yeah,
and the.
but we will.
Okay. Well.
2 here. 2 here.
Something there.
2 here, because the derivative of the bottom will just be 2x, right?
And the x.
And a 2 here, which gives us negative 2x over
X squared.
x squared minus 3 squared. There, now I got it.
Wait, put the square. Put the squared in. Put the squared in the x squared minus 3. X squared minus 3.
Is it?
Yeah.
Oh, yes. You're right.
Oh, is this?
I erased it to change it, and then I didn't change it. Sorry.
It's
Yeah.
the same.
They are the same. It's amazing. Quotient rule works. Low d high minus high d low over low low. If you have a quotient, you need to do that. Now I want to show you something, though, folks. I want to show you something that can save you some time and grief. When you think the quotient rule should apply, when you don't really have to use it, you can use something faster. So consider this with me for just a minute. This problem right here. If I have f of x equals 1 over 4x to the third. You might think that's going to require the quotient rule, but it doesn't, because this is different from this in that this isn't two terms. It's a single term, so I can rename it as 1/4 x to the negative 3 and use the power rule. That's always nicer when you can do that, if you can move it. So the derivative of this then, after the renaming, the derivative is going to be negative 3/4 x to the negative 4, which is negative 3/4
X4.
over x to the 4th. And you can use the quotient rule on this if you would like, so that we can prove they're the same if you'd like.
No,
You can use the quotient rule on this. It'll be the bottom times the derivative of the top, which is 0, minus the top times the derivative of the bottom, which is 12x to the second, over the bottom squared, 16x cubed.
Cross the
Square.
Oh, never mind.
Okay, so what happened? Bottom times the derivative of the top,
I don't
minus
think you
top
was
times
in
the
the bottom.
derivative of the bottom.
4x cubed. Just
square.
simplify the negative.
Oh, yeah, I did the squaring. That was dumb. Should just be 4x cubed here, which gives you negative 12x squared over 16x to the 6th. Knock out what you can, you get negative 3/4 over x to the 4th. Well, you cancel what you can.
Nice.
This is quicker.
Yeah.
But I'm just saying, the quotient rule can be applied to this if that's how you decide to do it. But in this case, because this is a factor which is now movable to the numerator, you can use the power rule. Just saying. If you ever have anything like this is also a good thing to use the power rule on instead of quotient if you're really good with your algebra. If you have f of x equals 1 over negative 3 root x, you should rename that negative 1/3 x to the negative 1/2. Bring that up, because it's a factor that can be moved. Then apply the power rule to that. It's going to be quicker for you.
Nice.
Okay?
So that'd be 1/6.
Positive 1/6. X to the negative 3/2, because you got to reduce that by 1, which makes it 1 over 6
But
x root x, actually.
I guess yeah, can't do that. Well, it'd be actually cubed.
Because x to the 3/2 is the same thing as x to the 1 and 1/2. There's your whole x. Or you can think of it like this, if you don't like that. Think of that as the square root of x cubed. One pair of x's, 1 x comes out, 1 stays inside.
Okay.
All right. And you may leave it like that. You don't have to rationalize denominators in here. It's okay. You could actually, if you really wanted to, you could just leave this x to the 3/2.
I just missed a call from Gavin.
Huh?
I just missed a call from Gavin.
Okay, well, you can take it if you want, but you may have to take it out in the hall because I'm recording this and I want to talk over you.
I'll just go back.
Okay, I want to do example 6 with you because this example 6 is really easy when you've seen how to do it. But if you haven't ever seen it, a lot of people are really clueless. So let's take a look at example 6. They love to ask this question on AP exams and even ISU exams. Luckily, it's easy once you've seen it demonstrated. So what we have here in example 6 is something rather strange. It says u of 2, meaning a function written in x evaluated at 2 is equal to 3.
Oh,
U prime of 2, this thing's derivative evaluated at 2, has a slope of -4. Another function written in x evaluated at 2 has a y value of 1. And that same function's derivative evaluated at 2 has a slope of 2. The question is, find y prime of 2 if y is equal to u times v. Y equals u times v. We have to evaluate y prime at 2. That's what we want to finally do. We want to do y prime. We want to find out what y prime of 2 is. Which means we need y prime. right? We have no idea what u is in terms of x or what v is in terms of x. We have no idea. We just know that they're functions in terms of x.
But we can make a function.
We don't even want to put an x in here. We never want to see x in this thing. What we want to do is apply the product rule to find the derivative. The product rule will be
Derivative of u plus derivative
no.
of v.
Start out with the first one. Just write it down. First times the derivative of the second.
Oh, derivative. Times the second.
Not times.
Sorry.
Plus
Derivative of the second.
the second
Derivative of
times the derivative of the first.
Ooh, that was.
You're going to want to memorize these phrases as you go through. Every time you tackle another problem, make yourself say what the rule is so that you get it memorized by the time you're done with this assignment without having to really work at it. So, to find, when we have a product, to find the derivative, you have to take the first function times the derivative of the second, plus the second function times the derivative of the first. This is to see if you know the rule. And then, to find y prime of 2, we find u of 2 times v prime at 2 plus v at 2 times u prime at 2. That's the reason why these were all 2's. If they weren't all 2's, we wouldn't be able to do this problem. And so when we say u of 2, we mean to go to u of 2 and write down what its value is. That's the 3. This 2 right here is the 2 that it's equal to, not the v prime of it. That's the 2 there. And v of 2 is 1. And u prime of 2, this guy right here, u prime at 2 is negative 4. So y prime at 2 is going to be 6 minus 4, which is 2. You see how that works?
Yeah.
This is a good way to test to see if you know the rule, because you can't take any derivatives or plug anything in because there's nothing to plug it into. These are x and y values, and there's no x and y in this. Well, there's this. These guys are in terms of x, but you don't know what they are. This forces you to write the rule and then make these plugins. It's a great way to test it. It's an easy thing to see if you're right or wrong. You just have to check the number. You see what I'm saying? So this is a test to see if you know the rule. Now let's see if you could do this if y instead was equal to, with the same stipulation up here, if y was equal to v over u. Not u over v, v over u. What would y prime be?
Times the derivative of u. So u times the derivative of
U, v prime, yep. Low d high minus over u squared.
Oh, right.
Okay, now, what is y prime at 2? We can't answer the question than y prime at 2. If we said, what's y prime at 4, you'd be dead in the water, because you have none of that information. But if they ask you what y prime of 2 is, where y was this quotient, then you use the rule and you make some substitutions. What is u at 2? 3. What is v prime at 2?
2.
What is v at 2?
1.
What is u prime at 2?
4.
What is u squared? U at 2 squared? 9.
2.
So the answer to this is going to be 6 plus 4, because it's a negative negative, 6 plus 4 over 9. That's the slope of the quotient curve at 2. You follow? Okay. The rest of it, I mean, I'm skipping some things because they're ridiculous to write again. It gives you the power rule again. It's kind of dumb. It applies to negative numbers as well, is what he's trying to say. If you have a function 3x to the negative 2, you can still use the power rule on that. F prime would be negative 6x to the negative 3, which would be negative 6 over x cubed. Okay? They're just saying it applies to negatives as well. I've already shown you that. The last thing, no. Oh, we still got time. We're going to do example 7, 8, and 9. We're going to do example 7 is a really good one because now that you know how to take a derivative quickly, we're going to apply it to writing equations of lines. What do you need to write the equation of a line? A point and a slope. What if I only give you an x value and a function?
It's okay. You can plug it in.
Then you go find the y value by plugging it into the function, the x value that we're looking at, right? That gives you your point. And then how do you find the slope of a curve? If you're in algebra 1, rise over run. If you're in calculus, how do you find a slope? Find the derivative and plug that x value in, right? Find the slope at that x value. Finding slopes means find derivatives. It's a slope generator. That's what they are. She said, now you know a quick way to do it without using a definition. So if I have the function y equals x squared plus 3 over 2x, this, by the way, using the definition, like the ones over there, using a definition on this would be a horrendous task. Thank goodness we now have a way to find the derivative, which is...
Calculator.
No.
High, low.
It says at the point 1, 2. So they're giving us the entire point.
Oh,
That's nice of them. If they didn't, if they only told us x equals 1, we'd plug it in here and find the 2. Is that actually 2 when you plug 1 in? 3 over 2 is 2. I mean, 4 over 2 is 2. 1 plus 3 is 4. Over 2 times 1, 2. 4 over 2 is 2. The y value. But you might have to go find it yourself. Okay? They gave us the entire point. All we got to find is the slope so we can write the line. So we say y prime, because they gave it to us as y, we'll say y prime is equal to
2x.
bottom times the derivative of the top
2x.
minus
X squared plus 8. 1, 2.
the derivative of that is 2.
Oh, yeah.
Right?
Yep.
You remember how? Yeah.
Yep.
This understood 1 times 2 is 2, reducing that to a 0, which is x to the 0 is 1. Okay. Over.
4. 2x.
Okay. So we clean it up. What do we get? Actually, you know what? You don't have to clean it up. You can plug x equals 1 in right now, if you want. Okay. So that would be, if I plug 1 in right now, it would be 2 times 2 minus
1, 4.
4
Times 2.
times 2 over
4.
4. Can you do the mental plug-in of x equals 1?
Yes.
So you can plug it in right there. You don't have to simplify anything if you don't want to. And that is 4 minus 8, which is negative 4 over 4. So y prime at 1 is negative 1. So now we have a slope at 1 and a point. You have a slope at a point, you should be able to write the line. If they want the tangent line, you use this slope directly. What slope would you use if they ask you to write the normal?
1/2. 1/2. 1. Yeah.
1.
Negative 1 over 1.
What's the reciprocal of negative 1?
Oh, we're stupid.
Negative 1. The opposite of that is 1. You need an opposite reciprocal. But that isn't what they said. They said write the tangent line. So here's what we do. Y equals negative 1 times x minus 1 plus 2. That's negative x plus 1 plus 2. That's the tangent line. Look at this. Look at the graph, because I haven't got time to let you graph. Well, I probably would, but we're not going to. If you graphed that original function in your calculator and you graphed the line, you should be able to clearly see graphically that that line snugs right up against the curve at the point 1, 2. And it does. Look at the graph to the left of example 7. See it? That's what would happen if you graphed those two things in your calculator, the original function and the line that you wrote. If your line is correct, you should be able to graphically verify that it is, because it should snug right up against the curve and be tangent to it at that point, which it is. And if that doesn't happen, you better look at either your derivative calculation and take a look again, or the writing of your line and see if you made any mistakes. So that's a visual verification if you got the correct line. Y'all clear? Okay. Second and higher order derivatives. This is the one that Sam was asking about. I'm sorry that he's not in here.
We'll tell him to get in. Yeah, it's just Gavin. I'll take the call.
You guys can share it with him. Besides that, he'll figure it out on his own, I'm sure. There is a use for these higher order derivatives, but we're not going to discuss their usefulness today. We're just going to show you that you can do it.
Wait, what order?
You'll see. Y
Higher
equals
order.
y equals x to the third minus 5x squared plus 2. Okay, look at this, please. What's the first? And I say first because we're talking about different orders. What's the first derivative of this function?
X squared minus 10x. Yeah.
What's the derivative of that?
6x minus 10.
And what's the derivative of that?
6.
And what's the derivative? By the way, we do this when we put it in parentheses. It doesn't mean exponent. It means fourth derivative. We don't want to just keep adding tick marks. Or even, if you really want to, I suppose you could do this. It's supposed to be Roman numerals, but these are slashes, not really numbers. So I'm going to put a 4 in here like they tell you to, and that would be
0.
0. And then after that, it's stupid because the derivative of 0 is 0 forever.
Yeah, but I could say another 50th derivative.
Yeah. Yep.
Like 0.
The 50th order derivative of this is 0. You can tell. The third order derivative is how you say it. The third derivative or the third order derivative is 6. First order is 3x squared minus 10x. Function itself was cubed. First order derivative is a quadratic. Second order is a line. Third order is a constant.
It keeps going down.
And the fourth order is a special constant, which is 0.
So it just keeps on going down. Further
Yeah.
down as you read
Yeah.
it.
Every time you take a derivative, because we reduce the power by 1, every time you take a derivative of a polynomial, that's very restrictive. The derivative of a polynomial continues to reduce its power by 1 until you get to nothing. Okay? But this is how you say it. First order derivative, second order, third order, or just say the first derivative, the second derivative, the third derivative. That's fine. Because derivatives are themselves functions, they also have derivatives. And these have their uses. You'll see later. I just wanted you to be aware that they are there and you can do them and they're not very hard.
Nice.
Last thing, and this is a really cool example. I think you'll like this. Please don't look at the solution. Don't do yourself that disservice. Here's the scenario. Here's the scenario. We have an orange farmer, probably in Florida or California, somewhere like that. Get this orange farmer, and they're raising oranges, and this is what's going on with their production. An orange farmer currently has 200 trees yielding an average of 15 bushels of oranges per tree. That's significant. Do you know what a bushel is? It's a basket that was made for the convenience of someone being able to pick it up and haul it away without getting in the way of their feet, and that wasn't too heavy, but they could haul quite a bit. It's a basket about like this. It's got little wire handles on the side. It's usually made of wicker so that it's very light. You don't end up hauling the basket as well. It's not too much, too very heavy. Have you ever seen them like that? Bushel baskets are about this big around. They're about this deep, and they kind of come down a little bit like this, like a truncated cone. Okay? That's about a bushel. 15 bushels of tree. They're pretty mature trees.
That's like, there were no leaves, it's all oranges.
Yeah, well, pretty mature trees, pretty big trees. Okay, now listen. Shh. She is expanding her farm at a rate of 15 trees per year. We're talking the same production level per tree. So she's not growing them from saplings. She's getting full-grown trees and adding them to her orchard. If she didn't, we would have trouble doing this problem. So just go with it, okay? Even though it may not be realistic. She is expanding her farm at a rate of 15 trees per year while improved husbandry. What is husbandry?
They come together.
Yeah, breeding. Improved husbandry is improving her average annual yield by 1.2 bushels per tree. So each tree is now producing more and more and more. Okay, so she's not only increasing the number of trees producing, she's also increasing how much each tree produces. Yeah, it's great. It's working out for her pretty well. So the question is, what is the current instantaneous rate of increase of her total annual production of oranges. It means right now, what is her current rate of increase in bushels? Because obviously, her production's going up. She's improving, she's getting trees, and each tree is producing more. So, how could we figure out, how could we get a function that tells us what her production level is right now? That's what we need. We want to eventually answer how fast is it changing? What's the rate of increase in her production? We got to have a function to derive to answer that. How do we tell how much she is producing right now?
Number of trees times amount per tree.
Yep. Number of trees times bushels per tree. Okay. Right now, this is her production level. Right now, production is equal to,
3,000.
how many does she have right now? How many trees?
200. Yeah, 200.
And she is
15.
adding 15.
3,000.
15 per
Year.
year. What would you like to call years? I don't want to call Y because Y is reserved for other things.
T.
T is good because it's time, okay? So it's 200 plus 15T. Do you agree with that? That this is the number of trees she has given this many years from now?
Yeah. Right.
Okay.
Hold the phone. Hold the phone. Oh.
What is her rate per tree? How many bushels per tree is she? How many bushels are they producing right now? Are they increasing?
Yes.
By how much?
1.2. T.
Every year with the increased husbandry, right?
Yeah.
So this is a production, an entire production value, a number. If you give her 5 years, then that's how many bushels she's going to get in 5 years if she continues this way. Do you agree? This is a production level per year. I'm sorry. This is a production level as a function of years. You following me or not?
Yeah. In terms of bushels.
How fast is it changing right now?
15, then 12 T.
We need that. To ask how fast something is increasing, how fast the rate is going, what's the rate of increase? Not how many oranges there are. How quickly are they increasing? You need a derivative, because that's what the slope of a curve is a rate of change at that instant. Do you know what I'm saying?
Yeah.
Do you understand why we need this?
Yes.
What would you like to use?
U derivative T and V derivative U.
Good idea. I think I'm going to use product rule. I really don't want to foil that out with the numbers that size and with decimals. I'm just going to leave them the way they are. So, to find that derivative would be the first times,
The second.
which is
1.2.
1.2. The derivative of the second is 1.2. Yeah? And then,
The second.
what goes here?
Plus. 15. Plus 1.2 T times 15. Well, great. Now we have a whole bunch of crap. And that's all over
Algebra. It's not all over anything. This is the product rule.
Oh, you can just put it
So, right now, how fast is her production increasing? What do we have to find?
0. T.
P
0.
prime of 0, correct. Which is going to be
240.
200 times 1.2, that's 0. Plus 15 times
50.
15,
What is 15 times 15? What is 15 squared?
225. 200 times 1.2 would be 240, I think.
Yeah.
So it's 240 plus 225,
465.
465. 465 what?
Bushels.
Bushels?
Bushel per year.
Bushels
Bushels.
per year, because it's a rate.
And that's not even year.
So just right now, if the husbandry stuff works really well and she buys mature trees that are producing the same way the others are, she will increase her production level 465 bushels this year. She will increase it by that much.
Wow. Well, how many is she making?
I don't know, how many is she making right now? 200. 200 trees times 15 bushels a tree. What's 200 times 15? 3,000? Right now, without adding the trees or the increased husbandry, she's getting 3,000. She will increase it by 465 bushels this year with the extra trees and the extra husbandry.
But next year she'll improve it by
Put a 1 in, and you'll know what her increase will be next year by doing the same thing.
It's like an exponential growth.
It will be, you betcha. Well, I don't know about exponential, but that's gonna be 200 plus 15 next year. It'll be 200 plus 30 the next year. You know, it's gonna increase. So that's how you answer, how are things changing right now as you let T be 0, but you have to plug it into the derivative because that's the thing that predicts the rate, the operative word here, folks, rate of things that's happening. You have to have a derivative, which means you have to have a first function based on a concept. Okay, I think I'm done. Made it. Did you get him registered then?
I think so. Do you want to chat?
Yes, I will.
Now?
Somebody tell him about higher order derivatives.
I told.
Okay.
Yeah, I'm trying. Okay, I'm going to call him real quick. He's saying his advanced opportunity.
Okay, you can talk to him about that. I'm gonna check out ISU and see. Oh, sorry, the end of the stream. Sorry, this is a whole nother object. See you later. Bye.